Hello, everyone. Welcome to the Space News webinar on methane monitoring. At the recent 2023 United Nations Climate Change Conference in Dubai, COP28, international leaders called for speedy action to curb methane emissions and eliminate methane leaks by 2030. One of the keys to curbing methane emissions is spotting these emissions, which to the naked eye appear invisible. That's where satellites come in. I'd like to thank Ball for sponsoring this webinar. And we have a 1-minute video from Ball before I introduce our panelists.
Hello, everyone. Thank you for joining us today to discuss one of the most important issues facing our industry and the scientific community at large, which is how to better monitor global methane emissions and drive policies to reduce the concentration of this far-reaching greenhouse gas in our atmosphere. My name is Sarah Lipsey. I'm the Director of New Business in our Civil Space Business Unit here at Ball Aerospace, and we're excited to sponsor today's webinar. Methane is one of the key drivers of anthropogenic climate change, but dedicated efforts to reduce methane emissions now could considerably slow the impacts of climate change and help create a more sustainable future. In order to achieve this objective, we must first ensure that we have the necessary data to inform decision-making and then take action. Today, we're going to hear from a panel of industry leaders and experts who will share their insights into how remote monitoring of methane emissions via satellites will fundamentally improve our understanding of the scope, sources, and impact of methane emissions, and how these data can be used to spur meaningful change now and in the future. Now, I'd like to hand things off to our host and moderator, Space News correspondent Deborah Werner. She will kick things off and introduce our panelists for today's discussion.
Thank you. We have a very impressive panel of experts here, some of the world's experts on this topic. So impressive that I'm going to explain briefly who they are, but also put links to their bios in the chat, and they're worth looking at. We have Dr. Shobha Chandragunta, Aerosols and Atmospheric Composition Science Team Lead at NOAA's Satellite and Information Service. Dr. Chandragunta serves on the White House Office of Science and Technology Policies, Air Quality, and Community Research Subcommittee. She has a PhD in atmospheric chemistry from the University of Maryland. Riley Duran, Chief Executive Officer for Carbon Mapper and a research scientist at the University of Arizona. Riley is also an engineering fellow at NASA's Jet Propulsion Laboratory. Dr. Robert Green is the principal investigator of NASA's Earth Surface Mineral Dust Source Investigation, known as EMIT. I'll try not to use too many acronyms today, but EMIT is obviously a useful one. EMIT is flying on the International Space Station, where it's been for a couple of years. Dr. Green has a PhD in spectroscopy from the University of California, Santa Barbara. Also from NASA is Dr. Andrew Thorpe, a research technologist at the Jet Propulsion Laboratory. Dr. Thorpe completed his PhD from the Department of Geography at the University of Santa Barbara, and his dissertation focused on developing techniques for mapping and quantifying methane emissions with airborne instruments. Dr. Stephen Hamburg is the project lead for MethaneSAT, and separately, Chief Scientist at the Environmental Defense Fund. Steve serves as Chief Scientific Officer for the United Nations Environment Program's Global Methane Studies and earned a PhD from Yale University. It's also worth noting that he served as lead author for the Intergovernmental Panel on Climate Change that won the 2007 Nobel Peace Prize. Okay. Oh, and I'm missing one, Jean-Francois Gauthier, GHGSat Senior Vice President for Strategy, who holds an MBA from Wilfrid Laurier University. So welcome, everyone, and thank you so much for joining us, because I have learned so much recently about how important this topic is. But instead of my explaining that, I would like to start by asking some of you, Riley, why is there so much attention now focused on methane?
Thanks, Deborah. By the way, quick correction of the record. I recently finally separated from JPL after 27 years, and so I could focus on Carbon Mapper, but happy to have gotten our start there and all the help we've gotten from NASA and other federal agencies that supported the incubation of our nonprofit program. But the reason why people are focusing on methane, it is truly a powerful greenhouse gas. It's often referred to as a super pollutant, second only to carbon dioxide, as a climate warming agent resulting from human activity. Additionally, it's important to understand that the growth rate of methane in the atmosphere is a cause of some concern. It is growing when we need it to be dramatically reducing as a result of efforts to reduce emissions. Methane is increasingly being targeted for near-term action, both because it has a very high global warming potential compared to other gases, and because of opportunities for rapid, targeted, and cost-effective emission reduction strategies that can complement other important climate stabilization programs like reducing carbon dioxide emissions. Often you don't hear about it as much, but methane is also an important pollutant from an air quality, a local air quality perspective. It is a precursor for tropospheric ozone, and it's often strongly linked with co-emitted reactive trace gases that can impact public health and environmental justice from frontline communities across the US and the world. It also occurs across multiple sectors, not just fossil energy production and use, but also the waste sector and agriculture. And it occurs across a broad range of physical scales, both individual high-emitting facilities, but also large numbers of low-emitting sources that manifest as area sources or regional emissions. And the last thing I would say about why people focus on it is that it often occurs both from a function of expected emissions, for example, venting and flaring, that can be expected, but often are wasteful, as well as unexpected malfunctions and leaks. And so it's important, if we're going to try to reduce those emissions, to understand where they are, why they're happening, and how they're trending over time. So that's why there's a focus on methane.
Shobha, I saw you nodding. Is there something you want to add about that? I think you're muted.
Sorry, Deborah. Yeah, thanks. Yeah, no, I was just nodding because, like, it's good that Riley tells the air quality component and relevance of methane to air quality.
Yes, and you focus on air quality also.
Right.
Got it. Okay. So, Rob, did you have anything you wanted to add to that?
I think O'Reilly said it most eloquently. He covered all the bases, and clearly it's an important greenhouse gas. I guess it's commonly referred to as having 80 times molecule for molecule the warming potential of CO2. And the other point I would add is that it has a shorter lifetime. So if we can get it out of the atmosphere sooner, then the impact in terms of reducing heating is reduced more quickly, whereas CO2 has a long lifetime. And so while it's very important, the return on investment in addressing methane now is just so clear, it seems to me, and I suspect others.
And maybe I can just jump in for a couple of quick additions. So just to be clear, that 80 refers to over 20 years as opposed to 100 years, which is the normal way. I completely agree. 20 years really matters. And then just to put it in context, methane accounts for about 30% of the warming we're currently experiencing. And as Rob said, the real key here is that we have two climate problems. We have the near-term problem. How do we slow the rate of warming now? And how do we ensure that we don't get too much total warming in the long term? Methane is the key lever for addressing that first one, how to slow the rate of warming. CO2 is going to dominate the total warming. So we have to do both. This is something we have to always keep in mind. Methane is critical to slow the damages over the next few decades. CO2 is critical to make sure we don't maximize, we minimize the temperature rise we experience as a globe.
And is there a problem with transparency right now? Steve, I heard you talk about this. Do we know where these methane sources are?
We don't know enough. We know we're learning more, but the key is we really need to understand around the globe, as Riley said, where are these emissions? And we also need to know how much those emissions are and how they're changing over time. We don't have that complete picture. We've got a pair of glasses, but they're pretty fuzzy. And what the satellites are will allow us, are already starting, but we will be able to do much more in the coming year or two, is to be able to put on a really much higher quality set of glasses and really be able to map that. And the bottom line is the satellites can answer two different problems, and we need to answer both of them, but most of them do one or the other or a bit of each. So the first is to do that mapping so we can understand the total quantity, the distribution, and track it over time. And the second one is having granular enough data about pieces, individual facilities, individual places, so that we can fix or reduce those emissions they occur. But that actually requires different data sets. And so we really need to solve two problems for the climate, and we have two types of data we need to drive the mitigation that we're all looking to accomplish.
So Shobha, how does NOAA monitor methane emissions?
Yeah, sure. Thanks for the question, Deborah. So I'm going to give somewhat of a long answer because there are various components to that. So NESDIS currently has like polar orbiting satellites, the JPSS series, on which we have an infrared sounder, whose measurements we use to derive methane concentrations. And these retrievals are really not sensitive to the near surface changes, mainly observe like the mid-tropospheric changes. So a well-mixed atmosphere sampled daily when averaged over time scales of months or years will provide atmospheric abundance of methane. So we can like look at like year-to-year variabilities and long-term trends. We can study those, and we've done that and we've published. But these are just concentrations, not emissions. So to get to the emissions, of course, you need to ingest these concentrations, assimilate them into a model to constrain the free troposphere, in our case, because our retrievals are sensitive to the free troposphere. And then combine with other in situ observations and so forth to get to emissions. So currently, all of this work is being explored at our NOAA's Office of Oceanic and Atmospheric Research Labs, in particular the Global Monitoring Lab. So there are some emerging capabilities that are taking shape as well. For example, Harvard University developed a simple algorithm to derive methane from our geostationary satellite imagers. These imagers have shortwave infrared observations. We can take advantage and then look at the methane leaks from facility level facilities and so forth. So one huge advantage of this technique, if the promise is realized, is we actually get direct emissions or fluxes from our imagers. Because what our geostationary satellite images do is just like take snapshots like every 5 minutes or 10 minutes. And then the time integration will provide you those emissions. So, but this potential for this technique is enormous, but we know where these sources are, like, where the pipelines are, where the natural gas compression stations are, where if there is a potential for leak, these geostationary satellite images are staring nonstop, so we can look at them, identify them. But again, this is just a new development that happened at Harvard University, so we are going to partner with it, with Harvard, and then try to bring some of those capabilities to NOAA. And I think like the importance of this is only growing because with the new methane rule from EPA, states, of course, have to develop implementation plans. It is possible that states may request NOAA to help with methane monitoring. So we don't know that yet, but it is possible because like in the air quality field, states do work with NOAA, use our satellite products in various ways for compliance and other applications. So we are hoping that this dialogue will continue, and then we may hear from states as well as EPA going forward for methane monitoring.
Thank you. We're also about to get more data. So Jean-Francois, I want to start with you because you've got a constellation in orbit now. Will you explain GHGSat for people who are not familiar with it?
Thanks, Deborah. So yes, GHGSat operates a constellation of 12 satellites that monitors methane and actually CO2 now as well. So our last launch of 3 satellites last fall included our first CO2 satellite as well. So we've been doing this since 2016, and we monitor methane emissions around the world and work closely with industry and governments to look at emissions and provide the best information possible to drive action.
Right. So Riley, will you tell us about Carbon Mapper?
Yeah, happy to. Carbon Mapper is a non-governmental, nonprofit organization that really spun out of a research and applied science program supported by NASA, primarily going back over a decade with a team I initially led at the Jet Propulsion Lab. And I want to emphasize that in tackling methane and greenhouse gas mitigation and monitoring in general, there's a need for, I'll say, a large toolbox, because the emissions that we're trying to help people reduce and understand and track and quantify occur across a wide range of scales, and there is a need for multiple tools in that toolbox. We need measurements that can provide continuous monitoring on the surface, handheld sensors that can measure very small emissions up at right on top of a piece of equipment. But we also need remote sensing, because remote sensing from satellites and aircraft have the advantage of seeing large areas and potentially can do it very frequently. And that's important because many of these emissions are often highly variable and intermittent. And the reason why we created Carbon Mapper was to address, as much as anything, an institutional challenge as a technical one. And if you think about it this way, an analogy to what we're trying to do, this whole community are trying to do with methane and greenhouse gas monitoring, is somewhat similar to the National Weather Services around the planet. And those systems that give us insight, continuous operational insight into what's happening with weather, have some parallels, and that is they combine different types of sensors in space, in the air, on the ground. And the difference here is that with weather services, were recognized as a high societal priority years ago, and they are very well resourced by governments. And so governments deploy monitoring systems from the land, from the air and space to measure the weather and all of its dimensions, and in a sustained and operational way, right? And Shobha's work at NOAA's Weather Enterprise is an example of that. Where we are today is a bit in the messy middle with greenhouse gas monitoring. We have benefited from over a decade of dramatic advances in research and technology that have demonstrated that these remote sensing technologies, for example, can provide actionable data, but they're not yet deployed at scale. And so in the absence of significant government funding to deploy greenhouse gas monitoring systems at scale, organizations like Carbon Mapper and EDF are beginning to apply non-governmental resources, in this case is funding from philanthropy, to begin to scale up some of these systems. And so the advantage of working as a nonprofit is we have the advantage to move quickly by partnering with industry partners like our commercial partner Planet Labs, like the work that GHGSat is doing in commercial space, have the ability to move quickly. And so our theory of change is by bringing together coalitions of other public sector actors like NASA, philanthropy, as non-governmental organizations, and working with the private sector, we can bring together different pieces of civil society to tackle what is a grand challenge. The grand challenge here being comprehensive, sustained operational monitoring to drive methane and CO2 emission reductions globally. And so that is our theory of change, why we created a nonprofit with a coalition of actors that is now a public-private partnership to launch our own set of satellites starting later this year.
So MethaneSAT also has an interesting coalition behind it. Steve, will you introduce that? Tell us a little bit about MethaneSAT and its partners.
Sure, thanks so much. So MethaneSAT, as Riley talked about, is a philanthropically funded effort. It was started to be able to really ensure that we had the data to take action. So it was explicitly designed, the satellite and the whole mission, to be able to provide actionable data to answer the key questions, primarily to that first question I talked about, really mapping the globe and being able to understand the quantity of emissions, the location of those emissions, and track them over time. so that we really can see the kind of progress and much better resolve where those emissions are coming from. Because we really don't. We have a rough idea, but we really don't know. There's lots of uncertainty, and we have to reduce that. And in order to do that, the Environmental Defense Fund created MethaneSAT LLC, which really brought together many of those communities that Riley talked about, though totally within a nonprofit context. So a little bit different model than the one Riley talked about, but related. So we partnering with Harvard University, with Steve Wussey, who he and I conceived of this project, to bring really the latest technology. So what we needed to be able to do to create that data is get greater precision in the measurements we're making. And so then we turned to Ball Aerospace to build the instrument and be able to get detection, so differences in concentrations at the surface of the Earth in terms of emissions as low as 3 parts per billion. And then all the data that we're producing will be made free. And we're building a very deep data platform analysis system that will allow us to convert, as Joe talked about, quantitative flux estimates. How much is being emitted where, not just the concentrations, which is traditionally measured by most of the satellites, because that's what we need for good, effective policy work. And I'll say we saw, as you mentioned in the intro, we saw at the Conference of the Parties in Dubai just a couple of months ago, a commitment to really address methane, and particularly from the oil and gas industry, where 52 companies said they would reduce their emissions to relatively low levels of 0.2%. The only way we can ensure that they meet those targets is to have the quantitative data across basins, across regions, to be able to track to see whether in fact they are complying with that commitment, because we need to make those reductions really soon. And we also brought in commercial space, and in the team that we built, we brought in academics, we brought in folks from government, and we will be launching very soon here in 2024.
Yeah, it seems like a lot of data is coming in addition to what's already out there. And when I talk to people around the world, they don't realize that a flood of data is coming that is going to make this easier to address. At least that's my impression. Rob, what's EMIT's role in all of this? Or Andrew, either one of you?
I can begin. So it turns out that EMIT, while focused on minerals, captured the same spectral range where methane and CO2 absorb, and EMIT has quite good signal to noise. So we discovered fairly soon after launch that we were a pretty good point source mapper for methane and carbon dioxide. So we presented this to NASA, and they helped us stand up a capability to focus and deliver products. So we've now mapped, I would say, more than 1,000. There's not quite 1,000 on our website, but 1,000 methane point source, and we're folding in the CO2. We're currently delivering enhancements, but we're planning to jump to emission rates as well, though the uncertainty when you have to bring in wind speed, as we all acknowledge, adds something. So EMIT is hopefully part of the Pathfinder and part of the contributor, as Riley and Steve have talked, and GHG representative. There's just a tremendous need for these broad set of measurements, because we live on a planet where orbital observations are challenging and clouds are challenging, that in my view, there can't be too many good measurements to contribute as we move forward. So I'll pause there.
Yeah, and just to build off of what Rob said, I think I do want to emphasize that, we've been at the Jet Propulsion Lab, been working in this field for over a decade or so. I think you alluded to my early dissertation work, right, using technologies like the AVERIS instrument, the airborne version of ultimately what's in space now, EMIT, to kind of demonstrate all of these capabilities. And we've been publishing, papers on every aspect of that going forward. I think one of the things that EMIT can really contribute to, especially right now, is the kind of a very high quality first look at certain parts of the world, right? So for over a decade or so, we've been using airborne instruments to map out methane emissions in places like California or the Southwest of the United States. Riley Duran was very involved in that early work at JPL and continues to do that at Carbon Mapper. But we just haven't had the ability to look beyond the US borders, right? And what EMET is able to do now is to look at different regions of the world, different emission sectors, and identify really fascinating methane plumes across these different emission sectors. And I think it's our contribution is, I think, really kind of a pathfinder to sort of set the stage, let people know what we're seeing, and for other organizations to kind of sort of take the baton and continue to push things forward when these other instruments launch, in the coming year.
Great, great. And there have been concrete successes in these various programs. So I'd like to ask some of you to talk about those. At AGU, Rob talked about Turkmenistan, and I know GHGSat has been pinpointing many sources. And Jean-Francois, don't you also work directly with the oil and gas companies to show them what's happening?
Yes, we work with oil and gas, the oil and gas industry on a daily basis to provide them with timely information that they can act on as quickly as possible. But also, and it's a theme that's kind of recurring when we talk about remote sensing for methane and trying to understand the full picture of emissions. And Dr. Hamburg often speaks about this. We have to have the full picture. To do that, we need frequent monitoring, because in oil and gas, emissions are very often intermittent, and it's really important to be able to characterize, are these persistent emitters, are they intermittent? So in our data, at least in a region like the US, for example, only about 15% of what we see is persistent. The rest is intermittent, can come and go. These percentages vary from region to region. In Turkmenistan, it's a completely different situation. Many of them are persistent. But the point is, using as many instruments as possible together to get the best picture possible is really key.
Riley, I see you nodding.
Yeah, 100% with Jean-Francois and others. This is back to my point about operational monitoring, and the analogy to the Weather Service is that, actionable data comes from being able to precisely locate it, the emissions, and to catch them, to see them. And again, remote sensing is a unique part of our collective toolbox, in that it can see large parts of the world, particularly satellites, without all the challenges of having aircraft, airspace and weather issues. But also the ability of constellations of satellites to do high frequency monitoring. Similar to the GHGSat experience, our experience in the US, detecting over 10,000 methane plumes with aircraft and satellites, we're finding that roughly half the time when we share our data with operators, where we can pinpoint individual emissions down at the scale of a few meters, but the operators report back that roughly half the time the emissions were previously known. These were permitted, process emissions, things like venting and flaring. And sometimes they say that those are more wasteful than they need to be, and they take steps to reduce the emissions. But the other 50% of the time, nearly half the time, they'll report that we didn't know about the emissions. And, just remember, methane is odorless, it's visible. And if you don't have the right kind of sensors, you would never know it's there. And so, quite a few operators report back to us that these remote sensing observations from above allow them to follow up and find and fix leaks. And in some cases, we're able to verify the leaks by tracking the emissions over weeks, months, and years that follow. And so, as some people would say, there's a there with this general approach. If you can find and guide people to fix the leaks, there are many cases they will be incentivized to take voluntary action, and as well as enable some of the new regulatory programs that are coming online, like EPA's super emitter program under the oil and gas rule in the US. So again, these are early success stories. I think it shows that there's a possibility to scale them up, but now we've got to follow through and do the hard work of implementation and sustain and build out these monitoring systems. And that's why we need an ecosystem. We need everybody on this call and others around the world who are also leaning in.
So I can also, sorry.
Good, please.
I was going to just talk about the International Methane Emissions Observatory, which has a program called Monitoring Alert and Response System, which is doing this on a global basis, working with governments to be able to take these specific large point source emissions and ensure that that data is getting out across the globe. Because you really need connections, you need to know who to talk to and all of that. And that's critically important. And Mars, I think, this system developed by IMEO, which is part of the UN Environment Program, is critical, I think, as a model of what we need to do on a global scale. But I want to also make sure that we don't ignore the part of the iceberg that's below the surface. So point sources are critically important, as everyone said, and we need to address them. But in many parts of the world, and certainly if we look at all methane, they only represent a small portion of total emissions. We also have to remember we're not just talking about oil and gas emissions. We have agriculture, we have landfills. And so we need, as Riley said, we need to have multiple types of instruments because we have to be able to see these diffuse emissions. Well, you could, let's say from oil and gas, say they're all point source, but they're, a very small emission coming off a pneumatic controller, a very small emission coming off a marginal well, which accounts for a very large percentage of the total emissions for oil and gas, for example, in the United States, and varying amounts across different basins. It's not a static amount. And so we need to create that whole picture. And then we can put these point sources and the critical important role it is to address them. But we need to be able to look at the total to ensure that we can hold folks responsible. One of the other wins that I think we're seeing is we're seeing multiple governments, financial institutions, and buyers of natural gas saying, we want to know how much is being emitted associated with a larger area, a company owns or a country. And we're beginning to start to be able to build that database so that we can really hold people accountable in a more generic way. And again, we have two problems. We need to do that broader as well as those specific point source emissions. And it's that tension or power of the synergy between them that will really drive change.
And just to
Robin, and oh, good.
Yeah,
Please,
just
Andrew.
to kind of follow up on Steve's point, I totally agree. I think measurements at different spatial scales are synergistic, and you can learn from measurements on the basin scale relative to the point sources. I did want to echo Riley's point about the need for more measurements right across the board. And so when we talk with stakeholders about our results and they ask us questions, often what they ask for or they request or they would hope that we could provide is total global terrestrial coverage at a very low revisit refrequency. And for context, EMIT has an 80-kilometer wide swath, and it generates about the coverage of Texas daily, not contiguous coverage, but it's pretty large coverage. But that's not enough, right? We need more instruments that are taking in more data so that we have global coverage with a revisit frequency that's sufficient for what folks need to do and for us to actually quantify these emissions, especially if they're sort of not persistent, right? So again, I think there is definitely a need for more measurements, and it's really encouraging to see this proliferation of this space over the last decade, right, to try to answer these questions.
Yes. Oh, good. Please.
Just want to add to the conversation here. So I think we are in a situation now where this marriage between public space and new space is happening, right? So in the CEOS community, the Committee of Earth Observing Satellites, we have new phrases now. Public space is for civilian satellites owned by national space agencies, and new space being the commercial satellites providing methane and carbon dioxide information. So this is exactly what we are talking. There is a marriage about to happen between these two entities because civilian satellites are like flying, like, they measure, but like they are somewhat at a coarser resolution. Clouds interfere with the retrievals. So the spatial resolution to observe methane is not as high as like some of these commercial capabilities. So I think at this point, we may want to talk about like, tipping and queuing, right? So these civilian satellites could like, potentially observe a leak somewhere, but then we can actually send a commercial satellite, like, to go zoom in and take a targeted look at a very high spatial resolution information. So I think like, you know, that is something will emerge where like there will be this partnership between civilian space and new space.
I think that's absolutely true and critically important. But I do want to say that MethaneSAT will have Tropomi, which is the European Space Agency
Right.
satellite that can do it, is got a 5.5 by 7 kilometers pixel. But MethaneSAT, when it launches in just a little bit, very soon, um, uh, will have a native pixel size of 100 by 400 meters and 200-kilometer wide swath with high precision. So it is at least we believe it's quite a big step forward in our ability to both marry those, but certainly tipping and queuing, because by having the wider swath, certainly then, and Riley and I've had this conversation many times, right? How do we provide the data to say, okay, let's go look places? And that's exactly what IMEO is planning to do. That's what Mars already does. So it's tasking when somebody sees something, whether that's a Tropomi or somebody, tasking as many point source satellites to go look at that place as they possibly can over an extended period of time. And it's important here to mention that the International Methane Emissions Observatory, IMEO, which I mentioned earlier, which is part of the UN Environment Program, is explicitly mandated by governments that fund it to bring all these data together, to create an integrated portal so that we can see these and integrated, because otherwise it can be confusing, because we have multiple data streams and we want to be able to help everyone be able to integrate that into a really useful set of products that everybody can utilize to understand the nature of the problem, as in addition to the specific owners. And then the last point I'd make, as I said, is that we're really in uncharted territory with respect to agriculture, pretty close to that in landfills, but I know Riley and Carbon Mapper have been working a lot, and GHGSat on landfills. But we're gonna see a lot with the data that we're collecting from MethaneSAT on agricultural distributions. And we've been partnering with the New Zealand Space Agency, and they have a program we're giving them targeting capacity within MethaneSAT. Well, they will be mapping agricultural emissions around the world. So we'll start to create a much more broader view of sources of methane, which I think will be absolutely critical to meeting the goal of seeing mitigation, and not just from fossil fuels, which is critical, but across different emission sectors.
Steve, a quick follow-up. What's the lead time to send a particular instrument, go look over this area? Like, is it like a day, less than a day? Let's say Tropomi, let's say Tropomi observes a leak, then how soon can we command a commercial satellite to go and look over the region?
Well, it varies from satellite to satellite. And it's going to be, numbers of days, because you have a latency of a few days before you can get the data. And then, of course, you have to be able to task the new satellite. And that's where this issue of persistence, right? So if it's a persistent source, no problem. It's intermittent. So that's why you want to keep looking at it repeatedly and see if it's, if you're seeing that same phenomena. But that's why, as Jean-Francois said, you want to have repeat measures. You got to keep looking. Just like we'll be doing with MethaneSAT, I think all of the satellite systems emit Carbon Mapper. We're all looking at it repeatedly to build a catalog that allows us. And in our case, because we can see the total emissions, we'll have a catalog and be able to actually tell you what proportion of the point sources are ephemeral, what they contribute, or intermittent, I should call them, and how that looks over time. And it will vary across basins around the world. This is a global problem, not just a US one.
On the tipping and queuing there, I can add some color, because that's something we've been doing for many years with the principal investigators for Tropomi at ESRON in the Netherlands. And the long pole in that tent really is getting the public data, because there are some delays at times. But once we have it, especially with now a constellation of 12 satellites, we can direct an observation, usually the same day or the next day, and then we can have results in under 24 hours. So it's a pretty fast process, and everybody understands that time is of the essence for these. As Dr. Hamburg just explained, if it takes too long, it's not actionable anymore. and we don't know, we can't understand if it's persistent or not. So it becomes very important to monitor frequently, to have the picture, but also to have data in your hands quickly so that people on the ground can actually take action.
Riley.
Yeah, just to add to this discussion, because it's also, I'm seeing some questions in the Q&A that kind of start to leak into this. I think tip and cue strategies, like where one satellite detects something and notifies another so you can follow up, is necessary but not sufficient for a couple of reasons. One is it absolutely makes sense when you're trying to follow up on a big event, particularly one that could be a public safety issue. But I want to underscore the need for thoughtful observing strategies. And I say that because, you know, what we're showing here is that you've got a diverse group of organizations that are deploying or already have satellites that are operational. But the degree of coordination is limited, not because we don't want to talk to each other, but because we're pursuing overlapping, but sometimes different objectives. And what that means is it doesn't, you know, there are very few satellites, almost none, I would say, that can see all of the Earth's land surface on a regular basis at the resolution required to address all of these use cases, right? And so what that means is that, you know, for the lay audience, you may not realize that even with these advanced systems, most of the planet goes unobserved because we have to make a trade-off between having very fine resolution and high sensitivity over key oil and gas production basins or facilities to resolve those emissions versus doing wide area of complete global surveys. And what that means is, unless we're coordinating up front about where we look and how frequently, is there can be gaps in space and time. And so you miss things. And so the chasing things with tip and cue is part of a strategy, but it's not a complete strategy. And I'm making this point because you can't just solve this with tip and cue and combining the data after the fact. So it's not just a data blending exercise. It is how do you come up with coherent, coordinated observational strategies? And that is a challenge going forward in our current approach, which is a bunch of independent organizations. So we talk to each other. And I think there is interest, and IMEO is one of the organizations I think looking to help. But I think this is where we need governments to help as well, is to set strategies on where should you measure to make sure that we're not all looking for our keys under the same streetlight, as we have to look under all of the streetlights and make our own streetlights where they don't exist if we're going to have true situational awareness. You can't fix it all after the fact.
When we talked about concrete successes, I'd like to ask the NASA folks about Turkmenistan, because that came up at the recent American Geophysical Union meeting in San Francisco, and is a concrete example of pointing out some emissions. And I believe from the imagery shown, much of those emissions were stopped.
Yeah, I'll be a little cautious there. Definitely the emit observations were delivered to all the communities, including the State Department. I know the State Department worked with the Turkmenistan government to look at the most persistent sources. And I think in the recent COP, Turkmenistan agreed to join the methane pledge. And our understanding from our colleagues at the State Department that the emit observations were strategic. And then I think there are other avenues being used to provide assistance in mitigating those large methane leaks. So yeah, that's one of many examples. But I think as has been the title of this this conversation is, it's an invisible gas. And so as we can make it visible, and a number of the methane plumes from probably GHGSat and from emit have ended up even in the press, that has an impact. And people realizing that it's colorless and odorless, but it can be seen, and we can encourage people to again focus as we provide actionable information at all levels and scales, and of course reaching into CO2 as well, help make those decisions and have actions taken to reduce methane right now, of which Turkmenistan is an example, and these observations are part of that activity and that effort.
And maybe just to follow up on that point, I think the EMIT results obviously were very significant in those conversations, but do want to emphasize that, there was a publication record that predates EMET's launch about, Turkmenistan having large methane emissions, right? And there were papers out of the Tropomi team that showed that. There was seen results from GHGSat, over the years as well. Again, so this is another example where you can learn things from other instruments and kind of inform what we're looking at on the ground in Turkmenistan. I would again want to emphasize that we're making all of our data available to whoever is interested, and that includes all countries, right? If we have acquisitions over countries, we will make that data available. Turkmenistan had a lot of examples, but other countries also emit methane, and we make that available. And it's really just about having people that want to use the data be able to access it and use it appropriately.
Great. We have some interesting questions coming in. One of them is about how the various, how MethaneSAT, GHGSat, and EMET compare to each other in terms of capability and accuracy. And I know you have different targets for those. So what would you like to say about those? Did we
We're not
start?
all jumping in here.
MethaneSAT?
I can start for MethaneSAT. So our goal, as I said, was to be able to measure basically all the methane there. It's obviously not literally true. We can't see all of it being emitted, but by having a very low detection threshold so that we can get a much higher proportion of the total emissions, and the detection threshold doesn't have a big impact. So to do that, we focused very heavily on having very high precision, as I said, about 3 parts per billion, which took a bigger satellite and much, much finer optics and the spectrometers and the detectors in order to accomplish that. And then also to be able to map it effectively over space, to have this small, relatively speaking, pixel size, which of course is bigger than for the target mode, and a wide enough swath so we can capture a whole region and we can understand the integration. So that's the approach. And to do that, we look at a very narrow slice of the spectra so that we can really focus on that. We also do CO2. We are just developing our CO2 products. We've been staying focused on methane as our primary driver for the construction and deployment of the satellite. And these steps would also allow us to, for the first time, get comprehensive data on agricultural emissions, not just oil and gas and coal mine.
And GHGSat, as I understand it, really is pinpointing sources.
That's correct. So it's a little bit different from instruments like Tropomi on Sentinel-5P. That's an instrument that measures absolute column concentration from the spacecraft all the way to the ground. And for us, we're really just concerned about the source itself. So we do measure the background as well, but we subtract the background so that we can get a value for the source itself. And as Dr. Hamburg mentioned earlier, like most satellites, we measure concentration. So that comes off in moles per square meter, which we can convert to parts per billion. But the value, the unit that's of most interest to most of our customers in governments and industry is a rate of emission. So we use different techniques. One of them is called integrated mass enhancement, to basically figure out, based on the wind, among other things, what is the emission rate at that source in kilograms per hour. So, and there's obviously an error rate associated with that. That can be several tens of %. It's not much different from most measurement techniques. There's always an error associated with it. And from our perspective, in blind testing, notably with Stanford University last year, when I say blind testing, I mean an amount of methane is emitted on the ground. It's measured at the same time, and then the values are compared. The measurement versus what's emitted on the ground, and we were in the range of about plus or minus 20% in terms of our accuracy. So this can vary with different regions of the world, different albedo conditions, but this serves to say that there is an uncertainty associated with those, but you can still get a value that's pretty accurate.
Yeah, and I might chime in. There are efforts to compare EMIT and GHGSat because we're both on orbit, and we have had opportunities, I think, funded from NASA as we want to do a comparison to look at the same targets. Now, that work is still in process, so not ready for publication. But I can say I've seen results where we see the same plumes in the same family. When they're observed in nearly the same time frame. So that's an important question. We do need to we all want to get on the same scales, and we want to have people have confidence in our observations to make those good decisions. We haven't had a chance to do a controlled release with EMIT yet because of timing and such, but we have airborne instruments where we've been scaling with controlled releases for them, where we control their observations, and then having those airborne instruments underfly EMIT, and that's part of our chain in tracing the accuracy. But intercomparison also very important. We look forward to MethaneSAT being on orbit. I'm sure EMIT should be still working, and will be opportunities for comparison there, and of course with carbon mapper as well when the Tanager series starts to fly.
I would say that again, because I feel like we're in the messy middle of transitioning from research frameworks to operational, is that there are efforts underway. I would say voluntary efforts within the remote sensing community to establish standards around methods for calculating and reporting and quantifying emissions. I'm talking here specifically about the point sources of their, I would say, companion efforts looking at the wider area of, the net emissions, to establishing publicly funded testing and independent evaluation and on a more routine basis, which is important for the growing constellation of satellites. And then last but not least is establishing intercomparison frameworks, again, perhaps hosted by the U.S. Greenhouse Gas Center. There was actually a workshop in Washington last week, hosted by NIST, looking at this with some of the federal agencies. And so I guess what I would say to the people on the call and the community is, bear with us. I think everybody is motivated to get this right and to improve confidence so that we have the maximum uptake and public trust in all of these systems.
And I might just add, I completely agree with all of that. And again, the International Methane Emissions Observatory is helping to coordinate internationally. So there is some controlled release experiments going to happen in Europe this coming summer. There's discussions in other regions, and to really build a global system of that. And as Jean-François mentioned, the single blind testing that Stanford at Adam Brand at Stanford's coordinated. I know Carbon Mapper, the airborne version, has participated. Methane Air, the airborne version of MethaneSAT, which has the same basic spectrometer, though not space qualified, contributed. And I think all three of us, certainly I can speak for MethaneSAT, we had extremely high accuracy and a very good precision across a wide range. This is for point sources. So a lot of the discussions, as Riley said now, is also how do we do a double blind? So in this case, you knew where you were looking. You want to get to a place where you don't know where you're looking, and you want to have diffuse sources as well. And you want to be able to go a wide range of emission rates. So all of that's in the works for all the reasons that Riley outlined.
Another person asks whether it would make sense to involve citizens to contribute to data analysis. And if so, what organization would undertake such an initiative?
I think it's always useful to bring citizen science in, but we do also have to find ways that it's going to be constructive for everyone. These are very, and I won't speak for any other mission, but these are very data intensive, computationally intensive efforts. We're totally cloud-based in ours, and we use a lot of computing power. So those types of analysis are really not well suited, but there are for looking at, for example, infrastructure in places where it's appropriate. Because one of the things we want to do is we need global maps of all of the infrastructure. And we've been working with various groups using AI techniques and machine learning to be able to build these maps so we understand what's out there. So then we can understand when we see things, what are the likely sources of those emissions if we can't directly identify the plume or the area emissions associated with an activity.
Somebody else asks, as the world warms and natural methane emissions increase, do the sensors have sufficient sensitivity and precision to distinguish sources against the rising background?
That's an excellent question, and it's a complex one. And I guess I would emphasize we've been talking here a lot about operational monitoring, for human activity, but this underscores the need for ongoing Earth system science. In particular, I'll pick on two sources of natural methane. One is high latitude methane from thawing carbon reservoirs. That's hard to do from space because it's dark up at high latitudes in the northern hemisphere a good part of the year, and secondly because of cloud cover. And so NASA has a major program called Above, which has been working on this problem for I think over a decade now, and international partners, and it needs to remain a focus because it is extremely challenging environment to measure. I'll just say full stop. And the other one's wetlands. Tropical wetlands are the largest source, probably, of emissions, of methane emissions, and they remain relatively poorly measured because, again, they can be hard places to reach, and the tropics are covered with clouds a lot. And so I think this is going to be a priority for not just the remote sensing community, but the earth science community going forward, is tracking what's happening as we see changes in climate-induced changes in terms of precipitation and temperatures, which will affect, in turn, the methane emissions from those important sources. So I just want to put a plug in for the NOAA, NASA, and other agency research programs, as well as what we're all trying to do.
Yeah, Deborah.
Oh yeah, please go ahead.
Just want to add to the challenges that Riley brought up. For NOAA, of course, to launch satellites, generate products, and so forth, we are driven by user requests. A user has to come to NOAA and say we need this product, and then NOAA will look into it and invest into it. One such request came from, for example, the Department of Interior to NOAA for methane emissions over Gulf of Mexico. But there is a big challenge to retrieve methane over ocean surfaces because the signal is weak. There are some special techniques like glint mode and so forth to retrieve methane in certain conditions. There's some possibility, I believe, but that's only depending on the certain times of the year. So I just want to throw back that question on challenges. How do we, when a request like that comes to NOAA, then NOAA is now trying to figure out how to address that request, but I also want to pose the question to the experts on the panel, how do we address that challenge?
Another question that came in is, how would an oil and gas company get in touch with any of these organizations, with any of you, to discuss data partnerships or information sharing? GHGSat, it looks like you've got a code right there.
That's a code to access our platform Spectra, to see examples of what we do around the world of oil and gas emissions, but also landfills, coal mining, above ground and underground coal mining. And we even have some examples in there. If I recall, I think we put an example of hydroelectric emissions in there, which is a little bit more on the unusual side, and some agricultural ones as well. So we try to show a cross section of our capabilities there. But in terms of how companies can reach out to any of those organizations, I think there's a lot of outreach that happens from IMEO, from ourselves, from EMIT, from different groups here to make the capability known and show that we're all out there to help and provide the data to drive, to help them better understand their emissions and characterize them, and eventually take the action that's needed. So I think we're all pretty active to let them know we're here, and there's various groups and discussions that are always ongoing on this.
And I'm sorry we didn't have time for all of the other questions, because there are some very good ones, but many of them revolve around how we marry these data sets, if there's a single organization that can validate methane concentrations. And it seems like Many of this remains to be determined, and many of you suggested there need to be greater global efforts to figure this out.
Absolutely, but I'm actually sitting in Paris because I have 2 days of meetings for the next 2 days on this very question. There is a lot of work to do that and being funded by governments to recognize the importance. And there are the TCON networks, there's a whole, we haven't had time to get into. There are lots of ways that the community is already collaborating, and someone mentioned CEOS. So we have to recognize that the key here is to not replicate, but to lean in and create the synergy across existing institutions and those that are getting built. So we don't have, so we make sure that we really do realize the gains that we collectively are talking about from this growing and rapidly improving ecosystem.
Thank you. Thank you all for participating. Thank you to our viewers and our webinar watchers. And also thank you to Ball for sponsoring this. Space News will be following all these programs, because I hope this is just the beginning of our conversation on this very important topic. So thank you all.